My name is Vishnu Prasad. I'm representing my research group from University College Dublin. My supervisor is Professor Alojz Ivankovic. So we are presenting our project on our research on interlaminar fracture properties of flax fiber bio-based composites interleaved with PPS wheels. As you know about the natural fiber composites, we have a lot of interest in the use of natural fiber composites, or especially the composite due to the lightweight and high specific properties. Again, there is an increased emphasis on the sustainability and the recyclability and the environmental impact of these materials used in industrial applications. Since we have a lot of interest on the sustainability aspect, we have focused our research on using the natural fiber composites as a reinforcement, also selecting a bio-based epoxy resin that can be recycled. So for this research, we used a polar bear-based resin that is procured from our concept company in Spain. So they have an acid clavable hardener that makes the epoxy to be recycled to a thermoplastic, which can be reused. So prior to this research work, we have done the recycling of this bio-based epoxy using mild acidic condition, which is already being published as presented in my citation. So moving to the current research, we are now focused on how to improve the interlaminar fracture properties. As we know that the natural fibers, they have very poor interlaminar fracture properties and they have poor resistance to the delamination. So the previous research works, which we have seen is basically on modifying the composites by producing a 3D weaving or stitching or Z-pignon technique. So this has incredibly improved the interlaminar fracture properties. But again, there's a question that the in-plane properties get affected by this Z-pinning or the stitching. So the next possible solutions are adding nanoparticles to the system. But again, like we have a limitation, that is when you go for a mass production, toughening this epoxy resin with the nanoparticles can be a challenging task that can produce number of voids and again cause a defect to the composite system. So currently, like what we have studied is the using of thermoplastic PPS wheels that has a lot of fibrils that can create additional mechanical interlocking between the fiber and the resin. So we have done this similar research on carbon fiber composites, and we were like interested to see how the system is going to behave in the case of natural fiber composites along with the bio-based resin. So, moving to the research work, the fiber is a flax, and we have a PPS wheel, and we have a recyclable epoxy. We'll be discussing more on how this composite system shows the results on the mode 1, mode 2, and the flexural properties. So this is the PPS wheel, or this is a polypropylene sulfide thermoplastic wheel. And on the right side, you can see the SGM images. So these wheels have fibril structure that can create some kind of mechanical interlocking and to some extent some chemical interlocking if they are properly heated or like at high temperatures. So currently we are going to see how they are done in room temperatures and under normal conditions. So we selected the resin infusion technique for the composite preparation, and then further we cut the sample as per the ASTM standards, and we performed that mode on interlaminar fracture toughness testing on these composite samples. So at every delamination, we note the force and displacement to find the interlaminar fracture properties at each delamination length, and finally we found the average interlaminar fracture properties. Interestingly, for the results, when you see on as the bar chart, you can see this is the flax fiber bio-based composite without any PPS wheels, and you can see with the addition of PPS wheels. So we tried the PPS wheels at 3 different conditions based on the varying aerial density. So the first case is denoted as PPS 5. That means the PPS wheel has an aerial density of 5 grams per square meter. And moving on, we have PPS wheel of 10, and moving on, we have PPS wheel of 20. So these PPS wheel are supplied by Technical Fibers in UK. So they have stock as 5, 10, and 15 and 20. So we selected 5, 10, and 20 for this research work. So basically, what we are doing is that during the composite fabrication stage, we put a layer of PPS wheel in between the middle layers, where we are going to see the delamination. So in the practical application, when we make the composite, we can use these PPS wheels in between the layers. So the procedure is not like complicated. It is just an additional layer, and the cost of the PPS layer is also like less. So there is no like significant changes in the manufacturing process. That's an advantage of this research. So coming to the result part, we can see there is a significant, there is an appreciable improvement in the modern interlaminar fractal properties of that's showing up to like 33% for 5 GSM and 41% for the 10 GSM and 59% for the 20 GSM. So let's now look into the mechanism that has improved this interlaminar fractal properties. So looking into the SCM images of the neat Flax bioresin and 5%, 10%, and 20%, you can see the PPS wheel that is being pulled out, or that is being producing some additional bridging mechanism. So here, this is the microscopic image or the microscope image of during the live testing. We can see number of fiber bridging that was particularly noted for the 20% GSM. So this is giving an additional resistance towards the delamination, and the PPS fiber pullout, PPS fiber breaking, and the matrix tracking are some of the mechanisms that contributed to the improvement in the fracture properties of the composites. In the next stage, we were interested to see how this PPS introduction is going to give when the composite is being subjected to a shear kind of loading. So you can see we have done the test based on the respective corresponding ASTM standards at 3 different span length recommended by the standards, and we could see there was not a significant improvement in the fracture toughness of the mode 2 results. This might be one of the the shear failure did not the PPS wheel did not contribute in the shear failing mode. This can be the reason. And you can see it's very light. That is 1, 9, and 30%. 13% is fine, but it's not a significant improvement with the use. But again, like this is again like kind of producing an additional resistance to the shear failure. So when you come to the flexural testing, it was interestingly seen that again, the results are not in a higher margin, but again, in an appreciable range of 15 and 21% for the flexural strength and the flexural modulus for the introduction of PPS wheels for the 20 GSM. We can see that there is a lower value for the PPS 10 that might be due to the manufacturing defect. But again, if you see the variation in the result, it is matching with the PPS 5. So we have to do the testing again for the PPS 10 and check how this result, like there is a variation in the result. So concluding our research, I can say that the introduction of PPS wheels to the Flax fiber bio-based system has good improvement in the modern fracture properties and very slight changes in the mode 2 and a reasonable improvement in the flexural properties. So this could be a good system with some minimalistic addition on the composites without varying the thickness or the dimensions of the composites, without any additional steps or procedures or energy consumption during the composite manufacturing. So as you know, like there is a certain limitations when we talked about the PPS 10, we have to work on how the PPS 10 is going to give the results. And yeah, so that's about our work.